Good morning. Welcome to another session of EE403 Distributed Generation and Smart Grids. So in the last class we were discussing about various islanding scenarios and protection schemes. Today we will deal with protection issues of standalone microgrids, that is microgrids which are disconnected from the utility grid. So before we proceed further, let us see a quote by Mahatma Gandhi. The science of non-violence can alone lead one to pure democracy. So we are in module 3 now, and this session deals with the major protection issues of standalone. Here standalone, what they mean is the islanded microgrid. So this we have already seen. There are three feeders: feeder A, feeder B and feeder C. And feeder A has a circuit breaker CB1, feeder B circuit breaker 2, feeder 3 circuit breaker 3. There are some sectionalizing circuit breakers, and there is a circuit breaker 4 here to disconnect the microgrid from the grid. So let us see what are the major causes of power system failure. So you can see here a snake. So there are many causes for power system faults and failures. It can be broken underground cables, transformer failures, lightning, tree contact, birds, squirrels, snakes, insects, bears, bison and cattle, mice, rats and gophers, vandalism, even elephants. So this is an example where two lines are coming in contact because of this insulation worn out, maybe because of overcurrent or some fault. So this is a transformer which shows one winding has some completely worn out because of maybe a short circuit or maybe the oil getting leaked and a fire following. It can be due to lightning. So as per our power system regulations, if there is a pole, there should be a clear zone of 3 meters from the pole or power line, or 3 to 6 meters from pole or power line if the tree is less than 6 meters height. Maximum height is restricted up to 6 meters for a distance from the pole of 6 meters. Similarly, the height is restricted by 12 meters and more than 12 meters depending on these distances from the pole. Here you can see a failure or a fault is created by some nests or a short circuit by a squirrel, or again you can see a snake over here which creates a short circuit, or it can be an ant colony short circuiting cables underground. So the four main protection considerations are distribution system fault protection, protection of micro sources, then National Electric Code requirements for distribution transformer protection, and neutral grounding requirements. We will see one by one each of them. So let us start with the distribution system fault protection. This is called the distribution system. You can see there is an LV feeder, AC feeder, and here there is an LV, another feeder, and you can see PD1, PD2, PD4, PD3. All these are protection devices. It can be a fuse or a circuit breaker or a static switch. So these protection devices can be opened to isolate a fault or protect the system from fault. So faults can happen in this feeder or in this feeder or on the MV side of the transformer, incoming transformer from the utility, or it can even happen in the customer load or consumer load, or it can happen on a DC line within a, this is a, you can see LVDC network customer microgrid. It can happen, a fault can happen on this line also. So all these things are various possibilities. So you can see that the red dotted lines shows the protection zone, and this side, this gray colored broken lines shows the LV microgrid, and beyond this is called the MV site. Now in this distribution system fault protection, we will consider three issues. One is microgrid MV system protection, then low voltage fault clearing requirements and presence of dispersed DERs in a microgrid. So let us start with MV system protection. Medium voltage means any voltage between 2.4 kV to 34.5 kV. Now the grid may be connected, or the microgrid may be connected with the grid. We call it grid connected mode. So if there is a MV fault means you should understand that the distribution part is LV and the input side of the transformer is MV. So basically an MV fault means fault on the utility side. So whenever there is a fault on the utility side, it leads to currents of the magnitude of 20 to 50 times the maximum load current. So all the MV side, the fuses are typically set to operate rapidly within 0.1 to 0.2 seconds to protect the various devices. Now in the grid connected mode, if there is an LV side fault, it reflects fault currents of magnitude 10 to 20 times the maximum load current. So here also fuses are set for a time delayed operation within 0.5 to 1.5 seconds. Now the problem of the protection system in this islanded mode of the microgrid is, whenever the microgrid is islanded, there is a drastic reduction in fault current. So the fault current will be much lower than when it is grid connected. So an MV fault of similar magnitude in a standalone microgrid would result in fault currents of about 5 times the full load current of the system only. So the fault currents are very, very, very low. Now the distribution transformer fuses have inverse time current characteristics. We will see it in the next slide. So inverse time current characteristics means as the currents are high, the operation time will be low. So this leads to slower operation of fuses and probably impossible to coordinate with protection of the microgrid DR units. So you can see here 3 inverse current characteristics are given for a 200 ampere fuse and 100 ampere fuse and 60 ampere fuse. And you can notice here for a current of 500 ampere, this current, this fuse, which means a 60 ampere fuse will open first, then 100 ampere fuse, and then only the 200 ampere fuse will be opening. So this is an inverse current characteristics. So for a particular current, the lower ampere fuse will open first. So for faults on the MV side of the microgrids, it's easy to just trip all the microgrid generation. You just trip everything. But is it acceptable to trip all the microgrid generation for an MV fault? Yes, because it is cheaper and acceptable, because it is a second contingency. The first contingency is already the microgrid is disconnected from the utility, and the second contingency is an MV fault. So when during a second contingency, it is better for trip all the microgrid generation. It is preferred to selectively isolate faults on the MV system and keep the remainder of the microgrid operating. But you need more circuit breakers and protective relays, which will be expensive. Now, a microgrid may face different complexities due to a medium voltage side faults, which we will see in grid connected mode. If a fault occurs on the transformer side of an MV fuse, the fuse will blow off rapidly due to the high current, fault current flowing from the utility and disconnecting it from the utility. But the faulty transformer is still connected to the microgrid, so what will happen? So even though for the grid the fault is cleared, the faulty transformer is still connected to the microgrid. So for the microgrid, the fault is still not cleared, or it is an open phase condition. If the microgrid is in the islanding mode, if a fault occurs on the transformer side of the MV fuse, because it is already islanded, and I already told you, when it is islanded, the fault currents are only 5 times the full load current. So if a fault occurs on the MV side, there may not be enough fault current to blow off the fuse, leaving it again an uncleared fault. So these are major problems either in grid connected mode or in islanding mode. If a fault occurs on the main feeder of the microgrid MV system, it may be separated to clear the fault from the utility system. So immediately we will disconnect the utility. If the microgrid has a centralized generation, that is, the generation is not distributed, everything is centralized, then you have 2 choices. Number 1, accept outage due to second contingency, or 2, add additional protective devices properly graded with the centralized micro sources. If the microgrid generation is distributed, then another choice is also there. Install relays at suitable points in the LV network. We call it sectionalizing circuit breakers, such that each micro sources can isolate themselves from the MV system and continue to supply their local loads. If the microgrid architecture is complex, then protection coordination may be best achieved through an intelligent PCM, while individual micro source protection can protect the DERs without having to coordinate with any other protective device. So let us see what are the protection challenges. In the standalone microgrid, it is difficult to have location sensitive fault currents of high magnitude. That is the one challenge. It's also difficult to make the conventional directional devices to automatically adapt from a higher fault current level to a lower fault current from after suppression. This is a problem when the microgrid goes from the grid connected mode to the islanded mode. The fault current magnitude changes, so the protective devices should operate with the new fault current, and this adaptive type of fault current settings is difficult in conventional directional devices. Now the coordination becomes difficult if zero sequence current voltage products relays are used. Now the high impedance of the microgrid source may cause the operating times of 2 adjacent relays to nearly match. So which one should operate first is confusing, leading to reduced selectivity. So sometimes more than one relays might trip at the same time. So the proper selectivity has to be achieved by employing differential protection schemes around each circuit segment. Again, we need high speed communication to all protective devices that trip any faulted circuit. These are the references. Please go through them and get enriched. With that, we wind up this session. We will see again with another microgrid issue in the next class. Thank you very much. This is Dr. Unnikrishnan, PC, signing off.